Okay, thank you. So good morning, everyone, or good afternoon. Actually, it is here in London. For better or worse, Zoom seminars are a fact of life these days. But I think it is one of the sort of nicer things to come out of the pandemic is we are now kind of used to interacting with people at greater distances than we used to perhaps before that. So that's a great opportunity, and I hope that's something we continue on with. And I want to take that opportunity today to tell you something about how we can use all the excitement of the past few years surrounding the first direct detections of gravitational waves to test the laws of gravity that are governing the universe on cosmological distance scales. And we'll get into, in a few minutes, why we would want to do that and how we set about doing that. But to start us off, as someone was commenting, I thought I'd show you this really lovely visual catalogue of the first 11 event detections by the LIGO-Virgo detectors. And so you've got in the smaller panels here, 10 binary black hole mergers, and of course the one confirmed binary neutron star merger in that set down the bottom here. And what you're seeing in each panel is something called a spectrogram in the background. So that's a plot which shows the spread of frequencies involved in the gravitational wave signal as a function of time. Okay, and you can see that bright spread of frequencies chirp upwards towards the moment of merger. And then overlaid in the sort of foreground of that, you've got a best fit waveform in orange. Okay, so that's a model waveform for that event. And if you really squint, you can just make out a sort of faint gray band underneath it. And that's a sort of cleaned up version of the data. So it's been a really exciting few years. There are more of these events now continuing to accrue. And of course, there's a huge amount of science to be done with these. Now, today, I am going to bypass a lot of the sort of really fascinating astrophysics of these events, although we will touch on them briefly. And I want to tell you more about how cosmologists are hoping to use these data to do some tests of fundamental physics. So there'll be 3 parts to this talk. I'll start off with just a general overview of both the experimental status and also something about these modified laws of gravity, these extensions of GR that I'm talking about. In the second section, I'll talk about what's happened so far in this story, just from the gravitational wave data we have in hand already. And in the third and final section, I'll talk more about the future. What would we like to do next? And this will mainly be a review talk, but there'll be just a little bit of work in the last section from this archive number here. Now, on the right-hand side of the screen, you've got this really sort of brightly colored and slightly weird painting. This is from the physicist turned artist, Gregor Horndeski. And he likes to combine his art with his physics, as you can see by the sort of Lagrangians painted on the top here. If you don't know who Horndeski is and how he's relevant to this story, hopefully you will do by the end of today. Okay, so let's kick off then with just the general overview of where things stand at the moment. And we'll start with the experimental side of things. So the LIGO detectors are currently offline. And that doesn't mean they're literally unplugged at the wall, but it means they're not in observing mode, right? They're in engineering mode. And they were taken out of observing mode on the 27th of March last year, at the end of their 3rd observing run, or O3. Now, actually, that observing run was brought to a close about 1 month earlier than was originally intended. And that, of course, was due to the pandemic and for the safety of the people working there. So there was only actually quite a small loss in observation time, thankfully. And during 03, 56 new events were confirmed, and those add to the 11 I showed you on the first slide. What's happening now, of course, is the detectors are undergoing further upgrades to improve their sensitivity. And the fourth observing run, 04, is now due to start in June 2022 at the earliest. And that has been pushed back already by about 6 months, again, because of global events. So there's going to be a little bit of a hiatus before we start accruing more events again. However, whilst these numbers are building up slowly, it's already time to start thinking about the next generation of gravitational wave detectors, what we call the third generation or 3G. And these are really sort of scheduled for the 2030s era. So there's a number of proposals on the table. Cosmic Explorer, you've probably heard of, same sort of configuration as LIGO, but arms considerably longer. The Einstein telescope, slightly different configuration here in this artist's impression, triangular configuration. And the last I heard, the Einstein telescope was being sort of scouted for sighting in Sardinia in Europe. I think that's not confirmed, but that's certainly one of the locations they're exploring. And then, of course, LISA, the space-based gravitational wave detector, also a triangular configuration. But where things get really crazy is when you start asking, how many events will we detect in this 3G era? So with Cosmic Explorer and Einstein telescope sort of operating simultaneously, the expected rate is just under 1 million detections per year, right? Which is blows my mind every time, right? That will be an era where gravitational wave detection is almost on a par with electromagnetic astronomy in terms of being able to really survey the full population of objects, having objects that are a relatively sort of refined granulation in redshift, for example. And that opens up a lot of possibilities. For LISA, things are a little bit different because, of course, LISA is designed to study the mergers of massive black holes that live in the center of galaxies. And that's in the lower frequency part of the gravitational wave spectrum. So there are, of course, fewer mergers of those things going on. So ballpark figures for LISA between maybe 100 to a few hundred mergers a year. Plus, of course, lots of continuous sources that haven't merged yet. So lower numbers, but a completely new part of that spectrum opened up. And as I alluded to already, what I want to tell you about is how we can use these things for cosmology. And in particular, I want to focus on one of the major questions of current cosmology, which is testing the laws of gravity. Now, probably everyone has heard, at least at some level, about this idea of modifying the laws of gravity on the largest distance scales in the universe. Okay, so creating extensions of general relativity. And still, the main driver for that kind of theoretical work, I think, is still really cosmic acceleration. Right? We have a universe which is accelerating in a manner that's consistent with a cosmological constant that makes no sense at all based on what we know from other parts of physics. So a lot of these theories are still trying to provide a sort of richer, more fundamental explanation for that phenomenon. There are some motivations coming also from various parameter tensions in large-scale structure. So things like the Hubble constant tension. Sometimes people ask, is that a sign of new physics? Doesn't have to be, but people ask the question. And sometimes people even try and ask if you can kill two birds with one stone and explain dark matter as well as dark energy with a single extension of GR on cosmological scales. Actually, that last kind of task is actually quite hard to achieve these days, but nevertheless, I sort of include it here. So these sort of vast array of theories that have appeared on arXiv over the past 20 years or more. And the theories I'm talking about today are designed to modify the large scales of the universe, which is a weak field regime. Okay, and many of these theories are actually designed to reduce to general relativity in certain environments, like a strong field regime or dense environments like the solar system. And this is achieved by something we call screening mechanisms. And screening mechanisms is basically a name for a bunch of mathematical properties, mathematical tricks that we know how to build into these theories to cause this suppression. Now, if I had a whole other hour, I could sort of take you into the details of screening mechanisms. I'm not going to go down that side road today. So I'll just put up some of the names you might have heard of, the most popular screening mechanisms, just in case they ring bells from arXiv. And so the reason I'm sort of laboring this point about them affecting the large scales, these gravity theories, is to explain why today most of the tests I will talk about focus on gravitational wave propagation and not generation. Okay, so the cartoon picture you should have in your head is something like this, where both the source of the gravitational waves and us, we live in galaxies, so nice, dense, screened environments. And the current, at least the current mainstream thinking is that in those environments, general relativity should hold. Okay, so we expect compact objects to form and merge as per GR. But it's when the gravitational waves leave that host environment and travel into galactic distances to reach us, that is when they are expected to become sensitive to these deviations from general relativity. Okay, and mg, by the way, on my slides is modified gravity. So that's the kind of setup we're working with today. Now there's one more bit of setup that I need to do, and that's to tell you about the framework I'm going to use to describe these deviations from GR. So today I'm going to be working not with a particular model of extensions, but rather a parameterization. So that's a framework which hopes to capture a much wider range of models rather than just sort of focusing on one. And I'm going to work with a parameterization called Hondeski Gravity. Okay, and Horndeski was the guy who did the painting on the second slide, so that's why he comes in here. And he actually developed this framework back in the 70s, way before there was a kind of observational motivation to, mainly as a sort of mathematical exploration. So in a nutshell, Horndeski gravity is the most general theory of gravity you can write down that has, in addition to the regular metric of GR, one new fundamental scalar degree of freedom. Okay, and there's also some restriction about the order of the field equations, which is needed to sort of avoid various pathologies, but that's kind of not something we're going to jump into today. So you should think of this like a parent theory, which has many offspring theories. And a lot of the big, in quotes, modified gravity theories you might have heard of, things like F of R gravity, scalar tensor theories, Galileons, they're all just subsets of this Horndeski action. Okay, so they all belong to this family. Now you can write down a Lagrangian for Horndeski gravity, and I'm not going to show it today because it's really big and messy and not particularly illuminating. So we're just going to take that for granted. I do have it on a backup slide if anyone wants to see it later. But there's this messy Lagrangian containing our scalar field phi and the metric as per usual. And for today, we'll just assume a regular matter action. So we'll put dark matter in there too. So what we're more interested really in terms of modern cosmology is the dynamics of cosmological perturbations predicted by this action. Okay, we know already the expansion rate of the universe looks really like a lambda CDM model. But where there's a lot more freedom for new physics, for the signs of departures from GR, is in the dynamics of structure, right? The collapse that gives us the cosmic web. And so we're going to take the equations of linear perturbation theory from this big Horndeski action on an FRW background. And when we do that, what drops out of this action is a set of 5 objects we call the Horndeski alpha parameters. Okay, alpha K, alpha B, alpha M, alpha T, and alpha H. And I'll tell you what they all mean in just a moment. So the statement is, in these linearized field equations that are going to give us a lot of our predictions for the cosmic microwave background and large-scale structure, wherever there are new terms in this theory, terms that are not present in GR, those terms have a coefficient that contains one or more of these alpha parameters. Okay, so they are literally parameterizing the deviations, the modifications to the field equations. Now, just before moving on, I will note that I'm being a bit sloppy with my terminology here. I'm calling these parameters, but as I've indicated, they're actually functions of redshift. Okay, so don't let that trip you up. Unfortunately, the term parameter is just abused regularly in this context. Okay, so these 5 objects quantify typical properties of extensions of GR. So for example, alpha T is a parameter which controls modifications to the speed of gravitational wave propagation. Okay, so that speed we often write as CT, T for tensor mode. And we can set that equal to 1, the speed of light in the right units, plus this object alpha T. Okay, so if alpha T is positive or negative, we have a deviation from the prediction of GR. Okay, and alpha T being positive does not imply a violation of causality in this particular model, because having this extra scalar field in our universe basically changes the light cone structure. So it's not, you know, if you think that looks pathological, it's not actually in this context. Alpha M controls the speed of propagation, that's the one above. Alpha M controls the rate of evolution of the effective Planck mass. So many of these modified gravity theories will give us what looks like a time-evolving big G, a time-evolving strength of gravity. And of course, that's equivalent to a running of the Planck mass. And that rate of running is controlled by alpha M in the form shown here. Alpha B is the braiding parameter, and it tells you something about a particular interaction term, which I'm not showing, which mixes up this new scalar field with your metric. Alpha K is the kineticity parameter, and it tells you whether this new scalar degree of freedom has a very standard canonical kinetic term or something much more exotic, which again can happen in some of these theories. And finally, alpha H is the sort of trickiest one to explain. It quantifies a particular transformation property of some of these theories under disformal transformations. So a disformal transformation, if that's new to you, looks a bit like this. So the first term here, where we just rescale our metric by this factor omega squared, that would be the standard conformal transformation. And when you've got this extra scalar field kicking around in your universe, you're free to construct this second term here. And that's what makes it into a disformal transformation. Okay. And in a nutshell, what this parameter does is it sort of extends the range of terms you can have in this big Horndeski action. So these are the 5 parameters. And they're all 0 in GR, right? That's how you get the limit. And the statement is that any of these sort of scalar tensor theories I mentioned, anything in this family, just maps on to a setting, a particular specification of these 5 alpha objects. And that means if we can do some tests, try and constrain these alpha objects with data, one of 2 things happens, right? Because we're testing effectively this whole space of theories. Either we find something exciting and, you know, we've found evidence for modified gravity and you can probably get a Nobel Prize for that. Or if we constrain them all to be very close to 0, then we can say we've ruled out that entire space of possibilities. And that means anyone working on dark energy, things like that, has to think again, right? That hopefully would spark new ideas, because this mainstream chunk of the model space, which is scalar field models, would be ruled out, right? And that would be, in my book at least, a sort of theoretical step forward. So the game is to try and measure these things. And I'm going to encourage you to briefly, mentally snapshot these 2 parameters here, alpha m and alpha b, and put them to one side, because I'm going to tell you about the other parameters first, and then we'll come back to these 2. Okay, so I'm moving on to the second part of the talk, where we explain what's happened so far. What do we know about these alpha parameters to date? And it probably is not a big surprise to anyone here that the first kind of major thing that happens in this story is the detection of the binary neutron star merger GW 170817. Okay, and I think everyone's probably familiar with the basics of that event, so I sort of won't go too far in describing those. But you know what was seen, of course, is the gravitational wave signal shown in the spectrogram here in the middle panel. And correspondingly, the electromagnetic counterpart, which was seen right across the spectrum. But for our purposes today, we're most interested in the gamma ray counterpart. And so the top and bottom panels here show the flux counts into gamma ray spectrographs that were operating at the time. And you can see, hopefully, the slightly faint green line here marking the start of that gamma ray counterpart. And so, as was quite widely reported, the delay between the first gamma ray photons and the sort of measured merger time in the gravitational wave data is about 1.7 seconds. And if you think about it, it doesn't take you too long to realize we can actually use that measurement to bound any difference in speed of propagation between our gravitational waves and our photons, our gamma ray photons. And you'll remember that difference in speed was something we parameterized with that alpha t parameter. Okay, and I've put the factors of c back in just to make things clear. Now, because this event was very close by, you can do really quite a simple time of flight calculation. The sort of the flat space calculation, you know, gives you the right answer to a good degree of accuracy. You can do a more accurate one if you like. And what you find in the simple case is that the difference in arrival time between these 2 signals is related to the alpha t parameter and the distance as shown here. Okay, so plugging in 1.7 seconds and 40 megaparsecs for the mean distance, you quite quickly find a bound on this alpha t parameter that is incredibly tight, right? It is less than 10 to the minus 15. You can convert this into a 2-sided bound, and it just changes by sort of factors of order unity. So I'm just sticking with the sort of absolute magnitude today. And that says, as far as we can tell, gravitational waves are traveling at c to a very high degree of accuracy. Admittedly, this is only one data point, and it's a data point at quite low redshift. So we can't sort of rule out the loophole that something exotic is happening at high redshift, but that requires a bit of a fine-tuning argument to make it work, so we take it as somewhat unlikely. Now, actually, the bound I'm quoting here is the most naive bound, because this number actually assumes that your gravitational wave from, if you like, the sort of moment of merger and your gamma ray photon set off simultaneously. And if you are, or you talk to someone who models the mergers of binary neutron stars, you'll know they're very messy things, and that certainly does not have to be completely true. So likely there can be an intrinsic delay in the emission of these two signals, which can be something from half a second up to maybe maximum 100 seconds. So doing a slightly more conservative version of the analysis weakens that bound to about 10 to the minus 13. Okay, but it's still a really small number even after that, so the conclusions aren't really changed. So this one event, this one data point, had a massive impact on this landscape of extensions of GR that people are building. And so I tried to summarize just some of the results here in a kind of traffic light scheme. Okay, you don't need to know what all these theories are. These are just names of particular models. But there were some things, like the things in red here, that are completely ruled out by that one data point, because they cannot have gravitational waves traveling at sea. There are plenty of things in green which are consistent with that prediction. Now, that doesn't mean they're not constrained in other ways, but they aren't constrained by GW 170817. And then there's things in the middle here in orange, which have their parameters, they're constrained but not eliminated. So they have some now reduced range of their parameter space, which they have to stick to be consistent with the data. Okay, but this was big news. Now anyone working on theories of dark energy or extensions of GR has to think about how they're going to deal with this measurement, how they're going to fit that measurement. So that was the first thing that happened in this story. The second thing that happened about 18 months later came from a more theoretical perspective. So after GW 170817, there was quite a lot of interest in what we call beyond Horndeski theories. The terminology is confusing, I'll admit. What this actually refers to is the subset of Horndeski theories which switch on that alpha H parameter, which I said was the sort of formal one related to that disformal symmetry. And that's basically because this subset of theories had some nice properties. They could meet the gravitational wave speed bound, and they could also still accelerate the universe in a nice way, etc. So people were working on that subset. And then this paper appeared in which the authors showed that if you have this alpha H parameter switched on, your gravitational waves can decay into bosons of your dark energy field. Okay, so there are two decay channels shown here, where gamma is the gravitational wave, pi is the boson of the scalar field. You can even, make a nice Feynman diagram for it. And this immediately sounds like trouble, because the fact that gravitational waves are reaching us from hundreds of megaparsecs away, they clearly can't be decaying into other forms of energy at any significant rate. Right? Otherwise they wouldn't reach us. So there's a lot of sort of heavy lifting in this paper. There's a lot of field theory calculations that I'm not going to reproduce today, but I will show you just sort of one insightful result from that paper. So the authors present the decay rate of this channel here, which is actually the dominant channel. And it's given by this expression where P is a momentum, lambda star is an energy scale involved in this Horndeski theory. And the thing you really ought to pay attention to is the numerator, because it contains this factor of 1 minus CS squared, where CS squared is the speed of propagation of these pi bosons. Okay, now in Horndeski theory, you can compute that speed, and it's given by a really messy, complicated combination of your alpha parameters. So strictly speaking, there's another one of those fine-tuning loopholes here. If you tuned all your alpha parameters such that CS squared is 1, then this decay rate goes to 0, as it must do by Lorentz invariance, and there's no problem. Okay, but again, assuming that fine-tuning isn't happening, this result basically places a very strong constraint now on this alpha h parameter. And again, sort of plugging in the numbers, I'll just present the result. Alpha h has to be less than 10 to the minus 10. Okay, so it's another one of it's a similarly a very tight bound on another one of our alpha parameters. So this was quite an eventful 2 years for this kind of field. We went from having this nice 5-dimensional functional parameter space to play with, and quite quickly we lost alpha t and we lost alpha h. And by lost, I mean bounded to be very close to 0, subject to a few kind of caveats. And this has really then started the ball rolling on that idea I mentioned earlier, that can we finish the job, right? If we can get similar bounds on these remaining 3 parameters, that'll be this kind of significant result in closing off a part of the theory space. So in just a moment, I'm going to tell you what we want to do next to constrain these 2 parameters. And these were the 2 that I asked you to kind of put on hold for just a minute. So the running of the Planck mass and this braiding parameter. You'll notice I'm not talking today about alpha k. And that's because alpha k is the sort of really annoying parameter. So when you look at these field equations, these parameterized field equations from the Hondeski theory, alpha k is there. But when you take the sub-horizon limit, so you look at a scale that a galaxy survey in the next sort of 5 to 10 years could actually probe, alpha k drops out of the equations. It's only when you look at really horizon scale modes of the universe it's there, but even then it has a really sort of minimal impact on horizon scale physics. So at the moment, I think no one's got a very good idea on how to bound this parameter, because it seems to affect observations we know about really weakly. So maybe in future, someone will have a great idea. But for now, I'm just going to leave this one to the side and focus on constraining these remaining 2. Okay, so we are moving on then to the third and final section, where we talk about what next. What else would we like to do to finish this job of constraining these alpha parameters? And in order to talk about that, I need to present the equation that describes a gravitational wave traveling across an FRW universe. So not worrying about structure for a minute, it's only a very small correction to what I'm going to say. So an expanding universe in general relativity. So Hij is my gravitational wave. Of course, we know really hidden in these tensorial indices, there are the plus and cross polarization modes. We won't need to sort of separate those out today. And this is a wave equation, right? Second order time derivative, prime's a conformal time for me. And I've gone to Fourier space already. So this was a second order spatial derivative, but it's become a Fourier number squared. And there's a friction term here. So this is a damped wave equation. And our friction term depends on the Hubble parameter. So as our gravitational waves are traveling across an expanding universe, their amplitude is decreasing, they're being damped. That's the situation in GR. And so we want to ask what happens when we go to our Horndeski parameterization of extensions of GR. Okay, so let's do that. Okay, so there's actually only one major change here, and I'll note that I have applied the bound on the propagation speed already, otherwise there would be a change in this term. So the change that's left is in that friction term, and you'll notice it's picked up a factor of alpha m, which was one of the two parameters remaining that we wanted to try and track down. And your intuition should tell you if this is changing the friction, somehow, sorry, changing the friction term, that is, it should change the rate at which the amplitude of your gravitational waves is damping. Okay, and to make that a little bit more quantitative, I'm going to do a sort of quick and dirty solution of this equation. Okay, so the quick and dirty solution, we're going to write our gravitational wave as equal to some scalar amplitude h and a polarization tensor E. Without further ado, I will throw away the polarization tensor today and just focus on this scalar object h. Now we can write h as some GR prediction, whatever that is, and allow it then to be modified by a factor b, and we have to allow for a possible phase factor c. So you can plug in this ansatz solution. You do a WKB approximation. You can solve for B and C. And what you'll find is that C is 0, so there's no phase shift induced by this parameter. But B has the form shown here. Okay, so it's a little bit messy. It's an exponential where the argument contains an integral over this alpha m object. So somehow the integrated time evolution or redshift evolution of alpha m, which remember was our Planck mass running, is what's impacting the amplitude of our gravitational waves. Now, that's fine. We found out what B is, but to make progress, we really need to know what the GR prediction is. Okay, and luckily that's a well-known piece of physics. Today, I'm just going to take the simplest possible expression, which is lowest Pn order. We'll assume non-spinning binary and a circular binary. And in that case, the lowest Pn prediction for this amplitude is shown here, right? And it depends on the chirp mass to some power and the frequency to some power. And of course, this thing would actually then be multiplied by polarization factors. But what we are really interested in today is the object that sits in the denominator here, which is the luminosity distance. Now, luminosity distance is one of those cosmological distance measures. If it's not something you deal with on a daily basis, you just need to know that for a flat universe, which is what we'll be working with today, it's basically the co-moving distance to the source multiplied by a factor of 1 plus z. So that's the GR prediction, but we said that prediction is going to be modified by this factor here. So you can probably see what's going to happen when we multiply this object through here. It's going to be quite naturally absorbed into a redefinition of this distance sitting in the denominator. And now we have a new effective luminosity distance for our gravitational wave, which is modified from the normal luminosity distance by that exponential factor. Okay, and that means if we have objects like standard sirens, things where we have an electromagnetic counterpart to a gravitational wave, we can measure the distance on the left from the gravitational wave amplitude. We can measure the distance on the right from the electromagnetic counterpart, because we can convert a redshift into a luminosity distance with some assumptions about the cosmological model. And that gives us a handle then on this factor in the middle, which contains our Horndeski parameter, which changes the relationship between these two. So let me make that a little bit more graphical, a bit easier to sort of get a hold on. I'm plotting here the ratio of these two distances. And of course, in GR, that ratio is just 1 for all redshifts. And what I'm doing in the colored curves is I'm cranking up that Horndeski alpha m parameter. And yes, behind the scenes, I've had to make some kind of assumptions about the redshift dependence that are not important for this kind of toy plot. And what you see is that at higher redshifts, these distances then slip apart, right? They have a non-unity ratio. Okay, and that's the effect we're trying to pin down. Now, I've also got some data points on here. In fact, there's only one real data point, which of course is GW 170817. And then the rest are mock data points. Okay, and so we've got at low redshift some mock LIGO events, things like GW 170817 that could be observed over the next 5 to 10 years. And at high redshift, we've got mock LISA events. So this is the sort of LISA version of a standard siren. So where a massive black hole merger gives rise to some kind of electromagnetic counterparts, some kind of flaring or variable signal in the center of a galaxy that we can use to identify the host of that merger. And it's a little bit of a trade-off between these two sets of points, because on one hand, the LIGO data will probably be available on shorter timescales, right? LISA is 2030 onwards. But the LIGO data is at quite low redshift, so it's going to struggle potentially to get a very good bound on the difference between these curves. Whereas LISA data, because of its redshift leverage, is in a good place to place much stronger bounds on these parameters, right, where these curves have slipped apart. So what I want to do is make this toy plot into a bit more of a sort of quantitative forecast for you. Ask how well will we constrain this alpha M parameter with these data sets. And in order to do that, you need to build yourself these mock catalogs of data. And I spent a large part of 2020 really trying to understand how to model LISA events. I won't sort of repeat that whole experience for you, but there were two sort of salient points I just want to mention. One of those is that the population models for massive black hole mergers is still very uncertain. Okay, but broadly speaking, there's sort of a dichotomy between two kinds of models, which is light seed models and heavy seed models. Okay, and that seed, of course, just refers to the progenitor of those massive black holes that then grows over the universe's history. And whichever of these models for the massive black hole population proves to be true when we finally get LISA data, actually has quite a reasonable part to play in our results. So just to show you some sort of spread in the predictions, if you have a light seed model that predicts maybe 600 or so merger events over a 4-year LISA mission lifetime, here's a mock sample of those events in mass and in redshift, and the color here is showing the signal to noise of that detection. And just for comparison, here is a heavy seed model, and I will admit that I have picked the most pessimistic model just to kind of emphasize the difference. But if we only have in this heavy seed model maybe 30 detections over 4 years, you can see that literally the number of data points we're going to have is going to be much less, and of course that's going to play a role in how well we can constrain these alpha parameters. The second sort of relevant thing you have to worry about when you do this is these electromagnetic counterparts. Right, again, there's a huge amount of uncertainty as to what fraction of LISA sources will actually have some kind of detectable EM counterpart. And predictions range from 5% up to 50%. And so in the work I'm talking about now, we picked a sort of moderate model that has about a 10% prediction. And those are distributed in redshift in some sensible way. Okay, so what you're seeing here in luminosity distance and redshift, where the pale blue crosses are all the events in the catalogue, and it's just the dark blue ones is the slice of them that has actually a detectable counterpart. Okay, so this cuts down the number of usable events further. So that's what we're going to sort of put into our forecast for how well we can bound alpha M. But there's one more thing I want to throw into the mix. Okay, I've been talking for the past few minutes about this alpha M parameter, but you hopefully haven't forgotten that there was another one we were trying to track down as well, which was alpha B, the braiding parameter. And it turns out, whilst gravitational waves only feel alpha M, many of our sort of more standard cosmological electromagnetic observations are sensitive to both alpha M and alpha B. Okay, and there are tools for calculating these predictions. So things like the temperature power spectrum of the cosmic microwave background. And on the right-hand side here, I have a quantity called the growth rate. And if you haven't met the growth rate before, it's something we extract from galaxy surveys, so measurements of large-scale structure, and it tells you something about how fast that structure is collapsing in the universe. Okay, and as usual, the gray line is the standard prediction in LAMB-CDM. And you can see that by cranking up, in this case, both my Horndeski parameters, alpha M and alpha B, I can get moderate variations in the growth rate, or I can get, you know, some pretty wild variations in the growth rate. So I'm actually going to throw together not just the mock LISA data, but also some of our current electromagnetic data. So Planck measurements of the CMB. These data points are from some recent galaxy surveys. I'll also throw in some supernovae data points for good measure. Okay, and sort of skipping the details of the actual forecast, which is mainly just sort of technicalities, I'll skip straight to the results. So this is the headline forecast for constraints on those two parameters we were trying to chase, alpha M and alpha B, here shown at redshift 0. And the blue contour here is the 2 sigma contour for the electromagnetic measurements only, so galaxy surveys and CMB. In green is what happens if we add in those LIGO standard sirens. And you can see they're unfortunately not helping a huge amount because of their limited redshift range. But it's when we add in the LISA data that it really compresses down this contour in the vertical direction because it constrains alpha M. Now there's some sort of funny shape going on to this contour. You can see there's a sort of hard cutoff down here. And we know why that is. That's a theoretical restriction on this Horndeski framework. So basically models below this line suffer from ghosts and other kinds of pathologies. They're unstable. And there's a sort of softer bound up here, which is coming from the growth of large-scale structure. So that growth rate parameter I mentioned, if you really crank up alpha M without cranking up alpha B, you overgrow the universe. Stuff becomes collapsed in a way that's already ruled out. And as we said, gravitational waves are really doing the squeezing top and bottom. So the precise numbers are over here, but sort of the average, if you like, of all these constraints on alpha B and alpha M is a number about 0.2. Okay, that's the ballpark figure for constraints on these parameters. And so the last thing I want to do is give you a bit of a sense of how good is that? What is, is 0.2 good or rubbish? And so to try and kind of lay this out for you, if I'd done this analysis with just one binary neutron star merger, I would have bounded just alpha M in that case to about 10. So it would have been huge. If you use about 100 binary neutron star mergers, you get a bound of about 1. And as we saw on the previous slide, that's actually kind of comparable to what the current electromagnetic data gives you already. Now, I've been talking about current EM data, which is a little bit of a cheat because, of course, LISA is in 2030s plus. And so we really want to try and estimate what the future EM data will look like. We can't quite project into the 2030s, but we can talk about the next stage of galaxy surveys, such as LSST, or the Vera Rubin Observatory, as it's now called, which is one of our upcoming surveys that should last about 10 years. And the forecast from that by itself is that it'll bound these alpha parameters to about 0.2. So what you really want to do is put together the LISA data and the future EM data. And unfortunately, I don't quite have that number for you today. That's a work in progress. But making a sort of educated guess, you expect to get at least a factor of 2. And if you're lucky, maybe even an order of magnitude when you combine those data sets. So we could be looking at alphas of about 10 to the minus 2. Now it's 10 to the minus 2 and not 10 to the minus 13 anymore. So I think those first few results where really like a single idea comes in and completely rules something out, I think we've probably had those. I could be wrong, but I think from here on out, it's going to be a little bit more of a slog, a little bit more of a traditional kind of gradually pushing down into the parameter space. But based on what we know from current theories, constraints of about 10 to the minus 2 would be enough to make life very uncomfortable for most of the models that we have in the literature today, right? And that would achieve our aim of hopefully moving things on and sparking new theoretical ideas. Okay, so I'm going to leave it there today. Just to quickly summarize, I explained to you what these 5 alpha objects were. I told you about how 2 of them are more or less ruled out. I said there was one really tricky one that we don't know how to measure. And I told you then about attempts to try and bound the remaining 2. And I explained that gravitational wave luminosity distances are one good way to do this. And we hope that we can try and close off this remaining Horndeski parameter space. Finally, I'll just acknowledge that I have kind of left to one side today a lot of really nice astrophysics that actually goes into modeling these events. And as I've hinted, is actually really important for the cosmology and the fundamental physics here. And as someone who sits more on the cosmology sort of theoretical side, I actually had a great time learning about some of that astrophysics. Okay, I'll leave you with a few references and thank you for your attention.
Thank you very much. That was a wonderful, clear talk, and I found it really, really interesting. So the usual procedure here is for people to use the raise hand function to ask a question. And if you have a follow-up, then maybe write that you have a follow-up in the chat, or write finger or something similar. Okay, so first up is Eric.
Thank you for that. I have to agree with Jamie. That was just really a really clear, beautiful, really illuminating talk. Thank you.
Thank you.
I have several questions. I'll start asking a general one, and then Jamie can throw me back at the end of the queue for other ones. So I know, like before this talk, I knew the tiniest bit about the Horndeski framework. And one question that I've had about it that perhaps you can answer for me is how independent are the different parameters, in the sense if one can reach in, and can one kind of reach in theoretically a priori to just twiddle the dials on each one completely independently and yield something like a viable theory? Or is it the case that when you reach in and alter one, you really have, it's really the values of the others constrain it, or that constrains the possible values of the others in order to yield something like a viable theory of gravity?
Great question. Great question. So several statements. So, okay, in principle, you could reach in and twiddle the parameters to be any setting, and you would have a viable theory in the sense that it would be stable and free of pathologies, but it might not necessarily give a good cosmology. So then when you ask, what do specific models of gravity do? So things like F of R gravity, when you map them into this framework, they do often impose certain relations between these alpha parameters, but they're not fixed. So we have some models which will only turn on some of them, and might turn on two of them independently. Other models will actually equate two of them, for example, or give some relation. And perhaps sort of connected to that, one of the interesting things is that the data actually suffers some degeneracies with respect to this. So if I can, I wonder if I can get back in my talk. All right, Zoom's not playing ball. But when I showed you things like the CMB power spectrum, there are actually some settings of the alphas, if you turn them, several of them on in the right way, that they will not change the CMB power spectrum at all. So there's some sort of weird blind spots, if you like, to certain combinations of them. Does that answer most of your question? Or
that helps a lot. Thank you very much.
John, you're next.
Thanks. Tessa, first, thanks again for a beautifully clear talk. That was just fascinating and wonderful to hear. Mine's a pretty simple question. I'm trying to figure out what's happened to lambda in all of this. I take it that if the alphas are all zero, then we have a non-zero lambda determined by by the normal observations. Is the hope that some of these theories are going to give a better foundation for lambda, or is that precluded by the setup?
No, good. So I did slide over this point rather quickly. So I focused today on the dynamics of these perturbations, right? And I didn't talk about the background expansion. And really what I was doing when I was showing plots was I was assuming the background expansion rate is lambda CDM, because observations tell us it has to be something very close to that. So the game in these models is trying to build something that reproduces that lambda-like expansion as far as possible, but can still do something interesting in the perturbations. So when you work with the Horndeski theory, because you're doing it blind in the sense that you're working with a parameterization, you have to just fix the background to be lambda-like and then have the alphas. But if you were doing a particular model, of course, you wouldn't do that. You would have some concrete, evolving scalar field or whatever it is you want to do in the background that would hopefully replace your lambda. I should say that some people are a bit, some people, that's bad. Some models are a little bit cheeky in the sense that they slip a lambda in via the back door. So they have some part of the modified Lagrangian, which actually at the end of the day just turns out to be equivalent to a constant. And then you're sort of doing a halfway house where you have an effective lambda and you're trying to do modified dynamics on the top. Great.
Okay, we'll go to Peter and then Ramesh and then back to Eric.
I may have missed it, but so I apologize if I did. But I think you were mainly focused on the neutron star mergers as in the last part of the talks. That was right. That was what you were looking at.
I mean, yeah, in principle, anything with an EM counterpart, but then practically, yeah, neutron star mergers or the equivalent for LISA.
Does a black hole neutron star merger buy you anything that a neutron star merger doesn't?
Good question. So assuming obviously there's a counterpart, then it might buy us some greater redshift leverage, because of course the more massive your source, the greater the amplitude, and therefore the greater distance you can see it out to, see in quotes. So that would help, because I said that higher redshift is better for these constraints. So that's one thing. Did you perhaps mean on a sort of more fundamental physics level, like actual dynamics of the merger, or?
That's what I was wondering.
So because the theories that I'm talking about here are, as we said, have the assumption of screening, and that's sometimes realized explicitly and sometimes realized with a bit of hand waving. But the general assumption is that the merger would happen as per GR. And so I don't think the dynamics there would be expected to be different in any way than the GR prediction. So I don't think that would help too much. Yeah.
Thank you.
Ramesh?
Yeah, so I was following the logic of what you presented. And the way it went was the first two alphas, you had an observable that was directly proportional to alpha or some power of alpha. And because you can constrain these observables quite well, especially given the long cosmological lever arm, you kind of killed those alphas. So the first two disappeared quite easily. Then the other two alphas, the problem appeared to be that your observable is not proportional to alpha, but 1 plus alpha. So you need to measure something very accurately, even to constrain this alpha parameter to better than unity. And as you showed, you can do at best maybe 0.1, 0.01, or whatever. So the question I was interested in is it out of the question that we could find some observable for these two alphas that is directly proportional to alpha itself rather than 1 plus alpha? Some clever idea that, that the one can be somehow eliminated in the observable, because then I think you'll be in business. You will be able to put much better constraints on those alpha parameters.
That's a good observation, definitely, about the proportionality or the 1 plus factor. So obviously that's a broad question, so I don't have a well-defined answer. But one thing that is receiving a lot of attention at the moment, and we are looking into, is cross correlations between gravitational wave and electromagnetic sources. So rather than just literally having standard sirens where it's one object and one counterpart, in a sort of fantasy land where you have a million of these things, like we said we would get for the 3G detectors, we can actually decompose that into anisotropies like we do with the CMB and cross-correlate the gravitational wave mapping quotes with a galaxy map. And that will be sensitive again to alpha M through both the galaxies and the gravitational waves, and alpha B through just the galaxies. So that's a really exciting observable. It's because it's a cross correlation, it's really messy. And so I couldn't say for certain yet whether it's going to remove that kind of, in quotes, 1 plus factor. It'll be some much more complicated convolution of those predictions. So I realize that's not a crisp answer to your question, but I don't have an exact idea in mind, but we keep thinking.
Yeah, no, that's fine. Yeah, I didn't have a crisp question anyway.
Eric again?
So Ramesh, that made me remember a remark you made. I'm pretty sure it was you who made to me a few years ago, that astrophysicists tend to count 1,000 as being a quantity that's 1,000 as being of order 1. So you might that this might cause even more problems for the 1 plus parameter. Tessa, if I remember correctly, or if I heard you correctly, when you first were introducing alpha sub m, you said that it actually measures the possibility for a varying Newtonian gravitational constant, but then you immediately switched to, and therefore it depends on the running of the Planck mass. But the gravitational constant also depends on, in a sense, Planck length and Planck time. Why do you focus on Planck mass for alpha sub m if it really is the possibility of a varying Newtonian gravitational constant?
Okay. So I should say that, obviously these theories I'm talking about are built in a purely classical sense, right? So Planck length and Planck time don't get considered. And when I say Planck mass, what I'm really doing, and this may be an abuse of my terminology, is picking out the thing that's coupling to the Einstein-Hilbert term in the action. Which, of course, in GR is a Planck mass, and in these other theories can be some more a function, right? Classic scalar tensor kind of function, and that is what I'm then calling my effective Planck mass. So to reinterpret that as modifying the Planck length and the Planck time, I don't think I could. It's not really what I want to do. So it's certainly true in, sometimes we talk about there being two gravitational coupling strengths in these models, right? Which in GR are the same. And one is the object that literally sits by the Einstein-Hilbert term, and one is the object which determines your coupling to matter. And in some of these theories, those two are not the same. So would your Planck length and Planck time still be coming from the one that determines the coupling to matter, rather than this other object, which is now different from that in my theories?
Well, I think that would definitely depend on the details of the theory that you're considering. I don't think I could answer that in the abstract. Okay,
but sure. So reinterpretation as variation of other fundamental constants. I suppose you could do it, but that's not how we usually do it, and I don't have a good reason why.
Okay, no, that what you said helps. Thank you.
Eric, did you have another series of smaller questions, or? You're on mute now.
I did. If no one else wants to go, then
I actually have a
please.
quick question, Eric, if you don't mind. So
Please.
the fifth alpha, where you say it has little or no impact on observables. If it really is there no impact on observables, does it matter? Is it one of these things that is just, it's like a gauge or whatever? I mean, is it a true parameter?
Yeah, good question. So I can tell you from her first-hand experience, it certainly doesn't matter in terms of computing anything like a CMB power spectrum or a galaxy power spectrum. So there are codes that compute these, right, that I showed you results from, and you can set this parameter to 1 to 10 to 10,000, and it won't change those outputs. I have plotted the horizon scale modes, and it does have a small effect there. Could it be reinterpreted as a gauge? I don't think so. It has the same status as the other alphas. It's just that it appears with the terms that it multiplies have a lot of are very suppressed, basically, compared to the others. So it's sort of parameterizing the you could think of it like the relativistic part of those equations, which is often neglected in sort of typical galaxy survey scale computations.
Good, thank you.
Julius?
Thanks for the wonderful talk. It's a naive question, but yeah, simply because I don't know so much about this stuff. So when you introduced the Horndeski theory, you said that we have one new scalar and we have second order equations. Is there a way to get something as nice as the Horndeski space parameterized by 5 parameters if we relax those assumptions even further? And if so, can we get like similar constraints? What happens there?
Great, yes. This has been looked into, and I'm pretty sure it's one of these references down the bottom, which I can't remember which one now. I think it might be the 1604 one. Where we looked at trying to do this for other field contents, so vector tensor theory, even a biometric theory. And the answer is you can do it. So you can build these generalized frameworks. Things get messy pretty quickly because obviously you now have many more interaction terms you have to include in your Lagrangian. So your number of parameters or functions will no longer stay at 5, but it gets up to about 7 and I think 10 in the maximum case. And there's a table in one of those papers that lists the numbers. What is lacking is a formal proof that the theory is complete, in the sense that with Horndeski gravity, it is known that this Horndeski action that I didn't show has been proven to be the complete set of terms you can write down that obey the necessary symmetries for gravity theory. Whereas for things like the vector tensor equivalent, which is called generalized Proctor theory, it's not proven. So there's a set of extensive terms that someone, a set of authors has written down as, everything they can think of, but it's not formally completed. The constraints on the generalized Proctor do exist and are actually sort of quite analogous to what I've presented on the scalar tensor version. No worries, great.
Okay, well, before we jump back to Eric, I'm just going to insert one of my own questions here. So I was wondering about the sort of mechanisms for electromagnetic counterparts in the case of the LISA targets. So when you have the binary neutron star mergers, you talked about how the constraints that you get depend on sort of the modeling of when the gamma rays are emitted. And so I was wondering if, depending on what the mechanisms are for the electromagnetic emission in the case of the LISA targets, are there any concerns that sort of the details of the systems would sort of have an effect on the kinds of constraints you can get? I know with luminosity distance, there's these inclination distance degeneracies. Are there any, if you had anything to say on that, that would be interesting to me.
Yeah, thanks. Thanks. There's a lot of great points there. So yes, you're absolutely right about the luminosity distance inclination degeneracy. I didn't talk about that today, but that was sort of one of the other bits of painful LISA modeling we had to jump into, and is actually included, marginalized over in those plots I showed you. Of course, for LISA, that should be less of a problem because LISA will have comparatively good polarization data, right, which you need to eliminate that degeneracy, simply because of the way it flies and orbits around. So lack of polarization is a big problem at the moment because of the alignment of the LIGO detectors, but should get better soon. So on the production mechanism of the counterparts, obviously that's a big question in astrophysics, and I'm not a galactic astrophysicist, but it relies on there being, well, most models rely on there being some amount of residual gas that hasn't been evacuated from the center of the galaxies. Or yeah, potentially that's the main thing here. Or sometimes people talk about some kind of variable signal depending on what the black holes are doing in the center, that there might be some kind of electromagnetic pulse that has the same period. And from what I see from other authors, whilst there's debate about the number of systems that will actually have enough gas, no one or very few people seem to be saying 0. So we do expect there to be some proportion. I have one other point, but I've forgotten what it is now because I've forgotten the last part of your question.
So have I. I think I was just curious about whether there was any worry. I mean, if there's uncertainty, if there's that much uncertainty in how many systems are going to have electromagnetic counterparts, I wonder if there was any corresponding uncertainty about whether, the emission and what kind of constraints
I remember that
would be available.
So the other point I was going to make is that this need for a counterpart in our case is very basic, in the sense that as soon as there's something which identifies the host galaxy, job is done, because then you can just get a redshift of the host galaxy and that's all we need. So this particular piece of work is actually very insensitive to the details of what happens in that host galaxy, as long as something happens. So that shouldn't be too much of a problem.
Okay. I just know that when sort of arguing for the fact that you have in fact correctly identified the host galaxy, there's sort of a lot of work that goes in, you know, in the binary neutron star case. You have to sort of use the localization from the gamma rays, and you're already using a lot of the sort of multi-messenger information in order to argue that you have in fact identified the right galaxy with when you find the counterpart. But hopefully that's not going to be a concern.
Yeah. So you're absolutely right that, you know, no one's pretending it'll be a piece of cake to find the host. I guess some of the numbers that give hope is for Lisa, the localization really dramatically increases in the very last phase of observation. So literally the last few hours, you get down to 1 degree in the average case and maybe 0.1 degree in some cases. And of course, the number of galaxies that corresponds to varies hugely as a function of redshift. But that's pretty good. And for something like the Vera Rubin Observatory, which I spoke about, that has a field of view of 10 square degrees and is designed to be very sensitive to transients. So the hope is to use something like the VRO in tandem and have it, you know, with an alert of a few hours staring at the right patch of the sky to help find that event.
Okay, thanks. Eric?
So, when you mentioned that that we could rule out alpha sub h because in order to not have it be 0, you'd have to have fine tuning of and you showed us this long complicated expression, and that made sense to me, because in order to get, you know, that whole thing equal to 0, you have to set some dynamical, you have to really twiddle some dynamical parameters like the Hubble constant. It's not just one fixed thing. So, but you made a similar remark in passing that in order to get around the bound on a sub t, alpha sub t, you would have to do some fine tuning. But you didn't spell that out. I'm just curious. Can you say what exactly the fine tuning consists of? And is it the same kind where you have to get particular values of dynamically varying quantities to exactly cancel out, or is it a different kind of fine tuning?
Slightly different, and it would be great if I can move my screen, which has now got stuck because I do have a backup slide on this. I'm just going to stop sharing for a minute just so I can figure out how to get to a slide. Sorry about this. Okay, so let me try and reshare. Okay, hopefully you can see that. So to break this down, so have the, oh, come on, here we are. Have the Horndeski Lagrangian here, and this is how the whole thing looks. So this is not the alpha parameters which come out at the linearized level, but this is the actual Lagrangian, and it consists of these various pieces. So it's the sum of L2, L3, L4, which starts to get more messy, and of course GR is sitting in there. And by the time you get to L5, these terms are blowing up. And when you ask what does the speed depend on in terms of these G's, which are the parameters that sit in the Lagrangian, it depends on a combination like this. So it depends on derivatives of the higher order pieces, which was G4 and G5. And so to finely tune this speed, what you need to do is make these 3 terms cancel each other out. So you need to arrange for some relation between those last two bits of your Lagrangian such that their derivatives obey this nice property.
What is the derivative you're taking phi with respect to?
Time, physical time.
Oh, so this is assuming something like a Friedman-Robertson background.
Yeah.
Thank you.
And
I'm sorry. Go on.
No, I was only going to add, if I recall, because this question obviously did come up like in the aftermath. If I recall correctly, it's quite easy to get two of these to cancel out, and I forget which two. I think it's probably the two parts of G5, but then you require something really quite weird to get this piece to cancel with these two, because of the explicit dependence on the Hubble parameter. And so you have to get something that evolves in exactly the right way with H to have it happen at all times.
Okay, great. Thank you. And last, really, I hope, really simple question. In the chat, I noted that the 1604-01386 archive number you gave us, I don't think is the right reference.
Oh,
it's unless you're pointing to a paper on finite composition representations in algebraic logic.
No, I am not. That's interesting. I
was hoping you might be able to give us maybe the name of the paper or something else we can find it with.
Yes, apologies for that. That's a good spot. Of course, you never actually follow up the numbers from your own slides, and I think that must be a typo. So you can see what I might have been aiming for was not that one. I don't want to hold up any more questions or keep anyone online. I can certainly search for this number. If anyone else wants to leave or ask a question, do so whilst I'm searching. Or not.
I think most of my questions actually got answered in the progress of the talk. I'd sort of have a question and then you'd immediately answer it. So
that happened several times with me as well, which is a sign of a good talk.
I think I've got the one I was aiming for. So I'm comparing two numbers now. Yes, 1604-0138. You know what it is? It's 86 and not 96 for the last two numbers.
86 is what you gave us.
Yeah, sorry, it's 96 and not 86. There you go.
Okay, thank you very much.
Sorry about that. I'll fix that. And what that is that's the paper that I was describing to Julius, I think, which was the more general framework for including other fields, so vectors and tensors.
Okay, perfect. I really enjoyed that. Thank you very much.
No worries. Thank you for all the great questions.
Thank you again. This has been really wonderful. Yeah.
Fun to talk to.